Howdy! This is your friendly neighborhood physics teacher here, and we're going to talk about periodic motions or simple harmonic motions or oscillations or whatever you want to call it. So today, you've had this PowerPoint for a day, so hopefully you've gone through it. I'm not going to sit here and read everything. I'm just going to hit some key points. So motion is a repeating cycle. Hopefully you remember when I had the spring and it's going up and down, up and down. I'm going to be going back between PowerPoint and my OneNote, so there will be a lot of weird transitions, just giving y'all a heads up. And so the two big things that AP likes to focus on is oscillations, dealing with a spring, which we did play with. Well, y'all didn't have a chance to play with it, but y'all saw me play with it. And so if you have your spring going up, kind of hitting middle, and then going back down, and then going doop, 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 doop. So that is your oscillation. That's one full oscillation. You started, you went up, and you can sit there and keep going. And what you'll notice is it makes a pattern. And that repeating pattern is what you'll see. So, that repeating pattern is what you'll see. That's what makes it an oscillation. Now, there's some that'll sit there and you can start saying, well, it looks like it's a sinusoidal. If I can actually, if we sit there and continued. Some patterns do that. Some patterns will sit there and just kind of go back and boing, 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 bounce like that. So it's, of course, according to what the object is doing of how that pattern is repeated. But an oscillation is just a repeating pattern. So you're looking at your slinky. Another repeating pattern that they like to play is pendulums. So we kind of looked at pendulums a little bit when we talked about energy. So again, you have this repeating pattern that it goes up here, and then goes here, and then it goes back down, goes here, and it goes here, and it keeps going back and forth, back and forth, back and forth. And there's that repeating pattern again. Go back to the notes. We might just stay in here so we don't have to keep going back and forth. So you have the pendulum, even a vibrating spring, and or like a slinky or something. I usually have y'all play with slinkies. Miss Verona is supposed to have her kids play with some slinkies, and if we get that video, I'll push that up so y'all can see some fun slinking, kids playing with some fun slinkies, but you can also find that on YouTube easily. So that's when you kind of get into your simple harmonic motion. So basically it's dealing with that force that causes that displacement from the equilibrium. And you get into periods and amplitudes and cycles and all these fun words that you've probably heard before, but you're not very sure how that relates back to physics. Simple harmonic motion it's like a stepping stone to go into waves. So it's a little interesting to talk about oscillations without jumping in going, oh, we're going to talk about waves since we're not going that far this year. But we're kind of going to dabble in waves a little bit. One thing I want to focus on is frequency. So this equation is on your formula chart. So if you pull out your handy dandy formula chart, it's going to be on the short side, so not with the big long. It's going to be after all the words. It says like A is acceleration, big A is amplitude, all that. It'll be the second one from the top. And what you'll see, is T equals 2 pi over omega equaling 1 over frequency. So that's the equation that's on your formula chart. This part we're going to hold off for right now. So we're going to pull that out. And so we're just looking at our period equals 1 over frequency. You can manipulate to get that frequency equals 1 over period. And you're like, you're saying these words. I'm not. So your capital T is your period. The definition of period is how long it takes something to complete an oscillation. Okay, so period is how long it takes to complete an oscillation. Your little fancy F is frequency. And that's how long, or that's how kind of far it goes in 1 second. So frequency is focusing just in 1 second. Your period is for the whole entire, so this is like one oscillation or one cycle. So period, you think about it as one cycle. Frequency is just for 1 second. And they are definitely an inverse relationship here. Three-way. Yeah, relationship. Pretend like I can spell. So it's definitely an inverse relationship. Did not mean to cancel that out. That's going to be fun to find again. That's okay. So that's where this stands for. So again, 1 hertz is how basically 1 over a second. Frequency measures cycle per second. So pretty much how many cycles happen in a second. And then period is how long it takes to do 1 cycle. But yeah, there we go. So if we're looking at just mass on a spring example here, there is a relationship of force and your displacement, and that is your Hooke's law. All right, nope. So that's your Hooke's law. So we're going to go back to finding my OneNote since I closed it out, and I'm talented like that. There we go. Cool, right there. And you've seen this before. So force of the spring equals your Kx. This formula is on your formula chart too. It has little funky things. It does absolute value here. Has another little funky thing. If I can write the little funky thing. It has another absolute value here. So those, if you didn't know, I think I've told y'all, but those little arrows above things, that's just telling you it's a vector. So it has direction. And then the absolute sign just means direction doesn't matter. And the reason the absolute sign is there is because if you're dealing with a spring going up and down versus a spring going side to side, it's going to react very similar, and they just don't want negatives to get in the way to confuse people. So your Fs is just telling you the force of the spring. Your K, if you remember, is your spring constant. And that is constant for that particular spring. It's not like a set number, like I can say all of Earth is 9.8 or anything. So it's kind of like your friction, your coefficient of friction. It's constant for those two materials, but it's going to be different if you switch out materials. Same thing with the spring constant. It'll be constant for that spring, but if you switch it with a different spring, it's going to have a different spring constant. And then your X is just your distance from the equilibrium. Another thing you'll also see it be called amplitude. So you might see an equation that is written like this, because that X can be called your amplitude. Now, what is on your formula chart is in pink, but they might, when we start deriving things, they might try to make you say X is your A. So that's just a concept you need to know. So your X is just your amplitude. And if we go back to our lovely little drawings here. So yeah, so if we're sitting there drawing and we're continuing our little sign thing here, if this is our equilibrium, your amplitude is just that. So that's your amplitude. And it's also your x. So that's not a very pretty sine graph, but it works. So, or x. There we go. So yeah, see if I can move it without canceling it, closing it out this time. Give me my PowerPoint. Okay. And it's just like how stiff the spring is. That's all I was just trying to reminding you that. So that is Hooke's law. And it's just how much force it takes to pull the object back to equilibrium or push the object back to equilibrium. If it is hanging, remember you do have that force of gravity that's kind of counteracting your spring force, and when it's at equilibrium, they're balanced. Looking at your kind of force amplitude graph or force distance graph, it's, again, you're dealing with this lovely area under the curve mess because you can sit there and find work. You can sit there and find work. And because work is your force times your distance. And so yeah, and then once you sit there and play with it, you see that your force, you can find your force by doing area under the curve. So it's just 1/2 base times height. You plug that in, and you can actually get that your work is your, and if you know what that is your elastic equation, which again is on your formula chart. But it looks pretty much the same thing, and they just use a U instead of a PE. Potential, your U is potential energy. And so it'd just be 1/2 kx squared. So that's just your elastic potential energy. And all this should be kind of a review. You're like, I've seen this before. We talked about this during energy. We did. So, like I said, this unit should be a reminder. Like I said, they use US on but if you look in your textbooks, I think they use PE. So I'm trying to sort of use both since we're being a little bit reliable in the textbooks too. So again, mechanical energy, remember mechanical energy is just your total energy. So you have to think about what energy is happening when it's oscillating. Remember that oscillation is that up and down movement or that side to side movement if you're dealing with the pendulums. And so we have kinetic energy and our spring potential if we're dealing with potential energy. And so your mechanical energy, just you can simplify doing that. And this is where the A comes into play. So if x is position at any point of the motion and v is the velocity at that point, if the total energy is calculated from the maximum displacement, so maximum displacement, we're going back up here. So maximum displacement is here, we're trying to calculate from maximum displacement. We can find that the total energy in terms of the amplitude, velocity at A is 0. So your velocity at your amplitude is 0. The reason it's 0, if you remember, when we're sitting there trying to solve for, this has max potential, this has max kinetic, and then it goes back to max potential. And then it just kind of cycles. So your max kinetic happens at equilibrium because it's, it's pulling, it stops, and then woof, so it's moving its fastest at equilibrium. Nope, not steam. Okay. Jumping around too much. So you can get your total equilibrium to be just this. And remember, your A is interchangeable with X. And therefore, we can write a single equation for mechanical energy to be that these two equal that. You can manipulate, like if you want to solve for your V squared, you can sit there and manipulate your equation, and you can so you can sit there and actually solve for your V, and it'll be plus. Reason it's plus or minus is because of that kind of square root aspect. So at equilibrium, the system reaches a max speed. Therefore, K at this point equals your kinetic. So your kinetic energy equals your total energy, since your potential energy is 0. So you're setting those equal to each other. And then you can solve for your max velocity. So substituting into giving these equations, you kind of can do that. So again, it's just kind of showing you step by step how to manipulate some equations. So the last equation is exactly the same as the speed of a rotating object as seen on this slide. So if you sit there and rotate, you'll actually see you'll get a sinusoidal, quit jumping around, a sinusoidal graph. The maximum speed at your initial position, is the same as the speed of the object rotating around this circle. So that's how you can get your circumference over your period. So your 2 pi r, or 2 pi amplitude in this case, over your period. You can sit there and solve for your period, and you can get that your maximum velocity is your amplitude, the square root of your spring constant over mass. Now, that if you kind of put these two equations together, you get an equation that's on your formula chart. So on your formula chart, again, in the short little area, you see that the period specifically for your spring is 2 pi the square root of m over k. So that equation is on your formula chart. And you can get that equation by putting those two other equations together. So this, and again, it is period. I can write, come on. So that is your period. It's just specifically your period for a spring. The mass does matter in dealing with spring, and that is your spring constant. And the reason that 2 pi involved, because it does make a sinusoidal pattern. It does make that pattern, so that 2 pi has to come into play because of that. So again, you're just kind of putting those equations together to get that. Ta-da! Oh, look, there it is. So the period of the mass comes to this. Notice that the period does not depend on the amplitude, because when you put those two equations together, it does cancel out. So the amplitude doesn't matter about the period. So if you have a spring going down at equilibrium, they are balanced. When it's at max down here, your spring force is more powerful than your force of gravity, so that's why it accelerates upward. And then, of course, when it's up here, your gravity is stronger than your spring force, so it accelerates downward. This lovely equation. I've only seen one equation out of all, the one question out of all AP tests use this equation. So I really doubt out of the two questions you're given that they'll make you use this equation. But I'm still going to show it to you because, yes, I want y'all to see it. Now, this equation is on your formula chart. It's actually in the version, It's the second to bottom version. It's this version. Let me write it down for you. So it's your x equals amplitude cosine of, please write, 2 pi frequency, come on, right, frequency t. So this is your distance. So this is your actual how much, like if you took a particle and how much that particle moves, that's basically what you're getting here. So it'd be, if something's going in a circle, this would be your circumference. Amplitude is how far it is off of it. Again, it makes a sinusoidal thing, so it's got to be like your 2 pi. You have your frequency, and you have time. So it's little t, so it's actual time, not period. And again, I have only seen like one thing use this equation, but I just wanted to show that to you. So this is the version that is on your formula chart, but that you can technically do it with period also, just substituting in. And like I said, like doing this, you're getting your sinusoidal function. So that's why you have that 2 pi in the mix anyway, because it's your 360. If you're in pre-cal, you kind of see that. So that's the only thing you have. If it makes a sinusoidal function, you kind of have to play with that. So that was just a brief overview of what to expect. I will later on do some practice problems, how that can relate, and maybe how a free response will take this information. Hopefully that helps break down your formulas for you, and I hope you have a wonderful day. Bye.